Hey kids, Smath here. Chapter 18 is electrochem, and a big part of electrochem is getting electrical voltage from a chemical reaction, a redox reaction where electrons are transferred. That's where that voltage comes from. And so today we're going to talk about galvanic cells. And galvanic cells basically have two or three parts to them, depending on how you look at it. They have a cathode. This is the site where the reduction occurs. Now you can see why we just reviewed redox. Reduction, oxidation. The reduction is going to receive the electrons. Okay, the cathode on this diagram is clearly labeled over here on the left, and the anode is the part where the oxidation occurs. And the way that I remember this is an, ox, red, cat, reduction cathode. And if that's the case, and you draw the anode on the left and the cathode on the right all the time, that's convention, then the electrons are always traveling clockwise. The electrons will always travel from left to right. Now, for this to occur, let's talk about what happens. This anode has zinc in a solution of zinc sulfate. So, and they've made it just so that these are standards of 1 molar solution. When we talk about standard conditions, we talk about 25 degrees Celsius, 1 atmosphere of pressure, 1 molar solutions. We'll find out later on what to do if these are not 1 molar solutions. But these are standard. So what's happening on the anode side of things is the zinc is going from the zinc metal. This is my zinc electrode right here. And those atoms are losing an electron, and that zinc is going into solution. Basically, for lack of a better term, the zinc is dissolving. It's dissolving in itself. It's going from an atom of zinc to an ion of zinc. On the other side, when the electrons make their loop and come around, okay, then they hit the cathode. That cathode becomes negatively charged, and that's going to attract the copper ions to attach to. How come? Because those electrons came down here. You had an electron there that attracted the positive, and now you went from copper 2 plus to copper. And in the process, up top, we have a voltmeter, which is going to measure the electrical potential of those electrons going through this circuit. And that's what this is. This is an electrical circuit. So if we look at these two reactions, we have at the anode, we have zinc going to zinc 2 plus an electron. And on the cathode, we have copper 2 plus 2 electrons becoming copper. That better be 2 electrons up top as well. Like all redox reactions, 2 electrons, they cancel. And what's my net? My net is zinc plus copper 2 plus goes to zinc 2 plus a little bit of copper. And we've described what's going on in this reaction. We haven't described the voltage of it yet. We're going to do that in a minute, but we need to look at the equilibrium of this reaction, because if we look on just the anode side, my anode side is going to become very positively charged. You guys can't see that. It's going to become more positive. And on the cathode side, it's going to become less positive. It's going to become more negative. And so in the middle, this one has what's called a porous disk, but a lot of cells will use what's called a salt bridge. And that salt bridge is a U-shaped tube salt bridge. This equalizes ion flow. So the salt bridge is a glass tube that has some agar gelatin in it. And in that agar gelatin, we've placed ions, usually something that's nice, soluble, cheap. Potassium nitrate works great. And because it's in gel, those ions are free to migrate. They can move. If we just did this as a solution, they'd all just plop out and that would be useless. But they're in a gelatin. And so the ions can move. Let's talk about how. If the left side, the anode side of this becomes positively charged, how can we balance that charge? Well, what happens is the nitrate ion migrates over to this side. And on the cathode side, it's building up a negative charge. It's less positive. So how do we replace the positive that was lost? The potassium. And so whenever we make a salt bridge, the cation goes towards the cathode and the anion ends up towards the anode. That's a good way of remembering that. Just remember the negative goes to the anode, the positive goes to the cathode. So we've done everything but figure out, where did this 1.10 volts come from? Well, there are tables of reduction potentials that are given, and these are listed in your textbook. And so if we look, we have a reduction potential of zinc 2 plus 2 electrons goes to zinc, the opposite. And that reduction potential is a negative 0.76 volts. We also have one for copper that is a positive 0.34. Well, we can see these are written as reduction potentials. Our zinc is going through oxidation. So what we do is we reverse this and we reverse the sign. Positive 0.76. Now if we take the electrical potential, the voltage, these are volts, we take the voltage of the anode, the voltage of the cathode, we add them up and we find out this is going to generate a positive 1.10 volts. So we just made a battery that's going to generate 1 volt of electricity. Is that of any use? No. I hate to break it to you, but these things are drawing a whole lot more than 1 volt of electricity. But this is the background of how we go about doing it. In the next video, I'm going to show you about how to calculate these cell potentials and what to do with them. When do we flip them? I'm Smath. I hope this video helps.